Hello everyone, welcome to this lecture of the course Digital Electronics and Circuits. And in this particular lecture, we will look into a state reduction problem. If you recall, in the previous lecture, we looked into a design of sequential circuits, clocked sequential circuits, and one of the design we built was that of a sequence recognizer, and we went through a multiple stages of design, right? Now, in this particular example, what we will do is, given a state table, right, we will see if it is possible to reduce the number of states in the system. And why reducing a number of states in a system is essential, because eventually, depending upon the number of states, only number of states will dictate how many flip-flops are required to be used in a circuit. And if at all we want to use a minimal circuit possible, wherever the opportunity presents, we need to look at any opportunity to reduce a particular state, if at all it's possible, right? So what we will do is we will talk about state reduction in this particular lecture, just to save some flip-flops, right? So now let's assume a circuit, right? I am just building a sample circuit where we say that we have a circuit something like this. Let's assume we have a state table and we have a circuit like where present state is. This is my next state depending upon input. X is equal to 0 or X is equal to 1, and this is the output. X is equal to 0 or X is equal to 1. Let's assume we have like 7 states: A, B, C, D, E, F, and G. Now let's assume when input is 0 and the present state is A, my next state is A, and when the similar situation in this case is it's B over here, it's C, A. Let's take an example of state reduction. And output, let's assume it's 0, 0. Okay, let's assume based upon a digital design, right? Based upon a clocked sequential circuit, we draw this state table. Can we, if we analyze, is it a possible to further reduce this table? Let's see that. So once we see that, right, we would be able to look into further circuit reduction. Now let's look at this particular circuit part, this line. My state E goes to state A when the input is 0, and it goes to state F when the input is 1 with an output 0 and 1. Same is the case with the state G. So basically this simply means that my G state is a redundant state and I can simply replace it by a state E. Right? So basically this at all is not at all used. It's not at all useful. So wherever G is used, I can replace it by E. Right? Now, as a next example, right? Let's look at these two particular states, D and F. Right? And once we look at D and F, what we will end up looking is my state D goes to E when X is 0 and goes to F when X is equal to 1, and similarly 0 and 1. Same is the case with F. It goes to E or F depending upon 0 or 1. And do we have D state going anywhere else? Yes, we have B going to D and C going to D also when X is equal to 1. Correct? So in this particular case, what we can do simply is we can say my F state is nothing but a state D, and I can simply remove this. Right? Now what we have done is we had, like, initially we had 7 states. Now we have reduced those 7 states into 5 states. And once we have done a state reduction, right, this will eventually help us saving some of the circuit combinational or sequential elements. In this particular case, if we have 7 states, we will need 3 flip-flops, log to the base 2 of 7. In 5 states also we would need 3 flip-flops. But the only thing is we are not able to reduce number of flip-flops. In case we would have been able to reduce the number of states to 4, we would have required 2 flip-flops instead of 3 flip-flops. But advantage over here is like we have a lot of unused states, and if we have unused states, right, we can take care of we can take advantage of x's don't care situation, and our k map would give us a further minimized circuit. I hope this particular example of state reduction was clearer, and how we were able to reduce some of the redundant states to minimize our circuit. Thank you.